Good morning, everybody. As she mentioned, my name is Kaz. I'm the Director of Research and Communications at SimTable, here today to talk about Realtime.Earth, collective intelligence from distributed imagery for environmental observation and modeling. This work is done in part by myself, Jamie Gould, Joshua Thorpe, and Stephen Guerin. We are out of Redfish Group and SimTable. We're based in Santa Fe, New Mexico, and we draw a lot of inspiration from the Santa Fe Institute and Los Alamos National Labs. Our work is grounded in complexity science, so we favor adaptive, emergent, and scalable systems over rigid and brittle architectures. We focus on enabling our users to form dynamic groups and roles to enable fluid interactivity. And philosophically, we believe that the browser is the new OS. And so we focus our development on browser-based technologies. The four here I'll be talking about today include live texture, which is our reality capture from cameras in geospatial contexts. Any surface are interactive surfaces powered by projection and camera pairs. AgentScript, our agent-based modeling library, all written in JavaScript. And then lastly, Asakia, our browser-based decentralized compute and storage module. So we couple these technologies in a variety of different configurations to empower our products. The two primary products we have include SimTable, which is our augmented reality sand table for geospatial phenomena modeling and participatory modeling. And that is a combination of any surface and AgentScript. Our other product is Realtime.Earth, which is our platform for collective intelligence, which draws from live texture and the Asakia. So we use these products to help communities explore and understand geosocial phenomena, with our work primarily being in the wild and fire space. We consider wild and fire to be a geosocial issue in the sense that we have an environmental problem that overlaps with social issues at large geospatial scales. Wildland fire is a complicated problem due to a myriad of factors, including climate change, land mismanagement, and disparate data points when it comes to observing fire. And this problem cascades into a variety of other issues, including timely and effective evacuation, post-fire flooding due to losses of vegetation and increased soil hydrophobicity, and evolving mitigation strategies that include prescribed fire, home hardening techniques, and landscape design. So unfortunately, we aren't very effective. We're effectively fighting blind on wildland incidents. Take, for instance, the Camp Fire from 2018. The fire started near Polga, this little yellow star right here, at about 6:45 a.m., and within 6 hours, the town of Paradise was nearly fully consumed. The fire was moving at a rate of about 1 football field a second, and with delayed reports of fire and a lack of coordination, circumstances like the following arose.
Paradise Police, how can I help you?
Are we supposed to be evacuated or what?
No, you'll be notified. There's a fire north of Concal, up off of Highway 70. No danger to Paradise, okay?
Well, it says evacuation west side of Pence Road.
What says that?
Butte fire.
Okay, we haven't been advised of that. If you have gotten a phone call or if you see flames or feel the need to leave, then do that at this time. But we haven't been notified, okay?
So more and more catastrophic events like the Camp Fire, the fires in Hawaii, and the LA fires are occurring with significant structure damage and considerable loss of life. But as you can hear, there's valuable information in the citizen, or that the citizen had, that could have been made use of by the dispatcher. So we feel the need to bridge the gap between citizens and emergency managers. And to that end, we ask ourselves, how can we improve intelligence during the first 3 hours of an incident? So real-time data streams relevant to wildland fire diversifying publicly accessible imagery such as the Alert California, Alert Wildfire, and Alert West camera networks are a great start to putting making imagery available to citizens, but they're only controllable by camera operators and designated officials. But we find a lot of value in imagery sourced from citizens, crews, and social media. With the ubiquity of cell phones out there in the world, and people's need to document such historical events, we see the potential of this array of imagery generated from these disparate sources, when leveraged collectively, can be your largest sensor array when it comes to providing information to first responders and the community in peril. So the fusion of these outlets we find essential for situational awareness. But we take a different approach when we think about recognizing there is a difference between what we call collecting intelligence versus collective intelligence. We like the idea of surveillance versus surveillance, right? So instead of having an instance where you have a single observer from above, we like to think of the collective set of folks from below, so surveillance, where we don't need to have a single common operating picture. It's not nearly as useful as many people think. We believe it's more relevant or pertinent to have multiple relevant operating pictures where not everybody needs to know everything, but people need to know what's relevant to them. Not even the incident commander needs to know everything that's going on. So everyone should have their own relevant operating picture. So to that end, to accomplish this, we are developing Realtime.Earth, a browser-based collective intelligence platform enabled by a decentralized architecture, dynamic group formation, and maximizing user privacy. Data silos are all too common in the emergency management space, and in many cases can be a disservice to both emergency managers and civilian communities. So the acequia allows us to push data to the edge and provide the capacity for increased data sovereignty. And live texture in tandem with acequia empowers our geospatial tooling that currently leverages Cesium, including tools to calibrate imagery, doing data derivation from this imagery, and information dissemination. So the tool is comprised of a variety of modules. The one I'll be talking about today is what's referred to as projective texturing. This is in essence taking calibrated imagery and draping it onto the landscape. However, Cesium does provide a ortho version of this. We are focusing on doing it with oblique imagery. So as you can kind of see here in this image, we have a cell phone projecting a texture out onto a three-dimensional model. But this allows us to contextualize imagery with respect to 3D tiles and other geospatial data sets. We can kind of think of this as a slide projector or like a flashlight. Imagine putting a transparency at the end of a flashlight and being able to shine it around the room. And we find that having it real-time and interactive is a highly important component of this. So it provides feedback to the users when they're fitting images to a landscape, when they're reconstructing events, and when they're attempting to derive data. So we've done this type of work before inside of a globe that we developed using Three.js. This is about an endeavor we started about 6 years ago. And for an instance of that, we have an alert wildfire camera. This was during the Adams fire, which was a small enough fire to not make it out onto the national scene, but it was highly impactful for this region. It didn't grow very large, but what we were able to do is document the progression of this fire. And using projective textures, we can, in essence, drape that imagery onto the landscape, combined with geospatial tools, can recognize the perimeter of the fire, shown in this yellow to red gradient, and the resources that were on incident, this cyan line, where a dozer was running down about 4:15. So it gives us a nice sort of augmentation of imagery, but also, again, be able to create a more coherent image of what's going on. So projective texturing in Cesium, our Three.js version was great, but we felt like Cesium might have a little bit more to offer us. So we started implementing projective textures inside of Cesium. It does have constraints, however, including having direct access to the shaders. Entities and primitives are not supporting dynamic positioning very well, and we're trying to restrict ourselves to avoid forking. That way we can kind of stay consistent with as Cesium evolves. So with those constraints, and after a couple attempts of messing around with primitives, we settled on using the post-processing stage. This allows us to run additional render passes after the main render pass of Cesium, and the output of that main render pass and subsequent passes get pushed onto the post-processing stage, and leveraging a custom fragment shader to implement this. So to paint the image, for lack of a better word, onto the viewscape, using the post-processing stage, we start with the main renderer. The main renderer produces a color texture and a series of depth textures, which go into the processing stage, along with the view camera that Cesium has. And beyond that data set provided by Cesium, we provide an image texture, which is the image we're looking to project, a depth texture associated with it, and a projective texture camera matrix. And with all those elements combined, using the fragment shader, we can produce a final view. So these elements, to walk through maybe a little more visually, what we have here is the first instance of a render pass where we have a viewer camera, and this is in essence its color texture here, and the white dot indicates a point in space that we would like to render with our projective texturing. So given this screen coordinate, we can kind of assume it's a ray pointing out into space. With the depth texture, we can go ahead and estimate the world coordinate or the world position of that screen coordinate. And from this main render pass, and the viewer camera matrices are used to reproject the screen coordinate into world coordinates. So now we know in space where that particular point is. From there, we can go back to the viewer camera color texture, and since we know that the screen coordinate's world position, we can now determine its relationship to the projective textures we're looking to project onto the landscape. So what we have now here on the right in yellow is a projective texture camera, and using this projective texture camera, the camera matrices, we can reproject the screen coordinates world position into the projective textures image space, and then use that to sample the color that we would like to put onto the landscape. So what we can determine whether or not is it within the view. If it's not within the view, then we'll go ahead, or maybe if the point is behind the camera, we will go ahead and not worry about rendering that area and just discard that particular UV. And at that point, we basically know that the world coordinate is within the camera's view space, but we haven't taken into account occlusion yet. So once we have this point sampled, we can go ahead and use some distance measures to determine whether or not the world coordinate is being, in this case here, can be projected onto the green mountain. Because it is visible to the camera. However, if the distances that we register with the world coordinate are greater than the distances measured by the projective texture, we know that there is some occlusion, that this point is beyond, in this case here, the orange mountain, and we don't need to render that. So to see this in action, this is a small video recorded of our projective texture of the Quarry Fire. This is a fire in 2024 in Colorado. This is imagery from the aerial resources that use the infrared to capture the state of the fire early on. And what we can see here is with this texture being projected and using Google 3D tiles, we can actually almost like look at individual trees and see which ones that were exposed to high intensity heat and its relationship to other areas that maybe did not receive so much heat, at least in this particular instance. And aerial imagery is great, but again, with our focus on citizen imagery, we captured some, we had some submissions here of the fire about a day and a half later, where using this projective texture, we can get a better understanding of perhaps what canyon was on fire at this moment in time. So you can kind of see here the flame front. It has a little bit of exposure on that front ridge, but on the back ridge, we see a lot more flame. So we can make an assumption that we have a flame likely up in that canyon. And then lastly, we have this image here of a map that was crudely drawn. You know, we have some pens and some markers. But we can leverage that once the image is calibrated, make it a projective texture, and see its relationship and overlap to the environment that we're looking at here. And these projective textures have some alpha blending, so we can kind of see all three textures used in tandem in this particular event. You can adjust coloring and transparency, but this is what we find super valuable, or one facet of the software we're working on being super powerful for augmenting the scene here. So, in conclusion, we believe that collective intelligence can help solve the dilemma of the first 3 hours using existing resources and decentralized compute. And for future work, we're hoping to enable more features in Realtime.Earth, annotation of GIS, which we've done in 3GS, but want to move into Cesium, live texture streaming of projective textures. Again, we've done that in 3JS, but would like to move that into the Cesium space. And then lastly, potentially a Sakia ion node that will do a lot of the 3D tiling. So with that, I'd like to thank you so much for listening, and I'll take any questions.